Welcome to the SEI podcast series, a production of Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the Department of Defense and operated by Carnegie Mellon University. Today's podcast is going to be available at the SEI website at www.sei.cmu.edu/podcasts. My name is Suzanne Miller. I'm a principal researcher here at the SEI. Today, I'm very pleased to introduce to you two of my friends and colleagues, James Edmondson and Sagar Chaki. They're going to talk to us today about distributed, adaptive, real-time systems. That's a lot of syllables, and so from now on, we're going to talk about it as DART. So Sagar, James, welcome. Thank you very much for joining us on this exciting topic. And before we get started talking about DART, why don't you each tell us a little bit about yourselves? Maybe start with Sagar.
Okay, thanks, Susie. So, I joined the SEI around 2004. I was actually a grad student, a PhD student at Carnegie Mellon School of Computer Science, and then crossed the roads and came here. So my research for my PhD dissertation was on a formal verification technique called model checking. Mm-hmm. And formal verification is this approach where you have a complex system like a piece of code, and you want to essentially prove in a mathematical way that it is correct, that it was written correctly and does what it's supposed to do.
And only what it's supposed to do.
And only what it's supposed to do. And that often ends up being one of the toughest challenges, is to express what you mean by what it's supposed to do. Anyways, I did my research there, and when I joined the SEI, I started working on applying software model checking to proving correctness of code and proving correctness of complex concurrent systems. And then we had a number of projects over the years trying to refine the technique and make it more applicable. We built a number of software model checking tools and put it out there. And then I think about 4 years ago, we started looking at this emerging class of systems called cyber-physical systems.
Yes.
And we were very lucky to have like a group at the SEI, a group of people with the talents to kind of tackle this very hard problem. So we had experts in real-time scheduling, we had experts in distributed systems, experts in software verification, etc. And then over the last 4 years, we've been slowly making our work more and more tractable, more and more sort of applicable. We're trying to do more examples, trying to put our tools out there. And so DART, which you just referred to, is a 2-year project, which started in 2014, and we're just sort of wrapping it up. That kind of is a culmination of all of this. It tries to bring together a number of different techniques, some of which James will talk about as well, to address this really hard problem of how do we engineer high assurance software for a class of complex distributed cyber-physical systems.
Okay, good. And James, what do you bring into this?
Yeah, so I didn't come from CMU, I came from Vanderbilt University, and my PhD dissertation was on distributed artificial intelligence and writing software and middleware for it, and also kind of trying to develop emergent systems as well, like things where you could design very simple agents and make something very complex out of it, or they have like an overall mission and they wouldn't be able to do it individually, but they do it as a group. And so I was very interested in pursuing research in capabilities like distributed artificial intelligence, especially in outdoor robotics, because that's a field that's really, really vague and ambiguous right now, and really not a lot of applied science in it. And so I came to SEI in, I think, 2012, somewhere around there, and started working on a project called SMASH. It was self-governing mobile ad hocs with sensors and handhelds. SMASH was much easier. And essentially what we're trying to do there was have one person be able to control a swarm of things. So we started with quadcopters, and we had them doing simple search, like for survivors and wreckage and rubble situations. I think we did a podcast on that before, so I won't talk too much about that one. But essentially, we had a lot of good success with that, and we showed 5 to 10 drones outside, or UAVs, I shouldn't say drones, outside just performing simple search. And then in recent years, I moved to using boats because they're just a lot easier to work with from FAA regulations, and also just with getting them working properly every time. And the students also can play bumper cars with them, and nothing gets broken, whereas a quadcopter generally falls from the sky forever.
And they're a little expensive.
I think actually what we've been doing has been pretty inexpensive altogether. We've been trying to work with really inexpensive platforms, partly because of funding situations, but also just because we think that it has the best impact possibility, because if you're doing something with $1 million UAV or something like that, it's very rare for someone to be able to pick that up, that research, and try it themselves.
Sure.
But if you're using like a Parrot Air drone, like for instance, which is like $300 or something like that, then you have a baseline that is more accessible for students, for research facilities and universities. And so with the boats, I mean, we're also talking about relatively inexpensive things, less than $1,000 for each boat, and that's important for us because a lot of what I do is trying to push us not only into multi-agent systems, so having more than one self-interested agent helping out with a mission scope, like extending the capabilities of one person, but also getting into kind of the swarm area, which is more 50 or more things. So, and this is kind of how Sagar and I met, and then started working together in MCDA, model checking for distributed algorithms. This was 2 years ago, 3 years ago? I guess it was 3 years ago
Dart,
now.
yeah.
So that was the precursor to Dart. And I was working on getting capabilities outdoors and having these distributed agents cooperating. And Sagar was working on formal verification, model checking specifically. We weren't working in statistical model checking yet at that time. But we were trying to do like a formally proven way
Sure.
of making them collaborate together and be able to check things like safety and correctness and all those kind of things before we actually deploy them. And this started another vector of my research, which is really about trying to bring artificial intelligence from simulation to reality. And we're talking about artificial intelligence, not in the case that you'd see in science fiction a lot of times where it's a nefarious thing. It's something that you control from the ground up, and you're really just trying to build something that thinks or acts rationally, reasonably, and can complement what you're doing.
Within a specific domain, typically. So
Yes.
it's not the general
It's not-
iRobot kind of thing. It's
Yeah.
within a very specific domain. There's a set of boundaries within the AI entity would work within.
Yeah, you don't have to worry about Isaac Asimov's rules of governance or any of those kind of things. This is the kind of artificial intelligence that has a very, very focused mission objective. It's usually very simple agents as well that are modeled as like finite state machines. Finite state machines, so they have a certain kind of rule set that they're kind of iterating over, and then they do that action whenever the environment is appropriate or where their collaboration status is appropriate. And then what we wanted to do was be able to simulate that at scale. So, a lot of the things that we'll scale are between 5 and 30 agents, let's say, participating. And then we wanted to see if that would transition into the real world, and we've had a lot of really good results for that.
Yes.
So tell us about what's the scope of DART, the project, and what you've accomplished over the last couple of years.
So as James was saying, so we had this precursor to Dart called MCDA, Model Checking Distributed Applications, and we kind of started exploring this idea of bringing together research in distributed systems, which is focused on capability, with research in formal verification, which is focused on getting assurance. And what we realized at that time, got really excited about, was this emergence of these class of systems that consisted of agents that are collaborating and cooperating, but operating in an uncertain environment to achieve some mission and safety goals. So a classic example is what happens in an Amazon warehouse. And I use this all the time because Amazon used to outsource this capability to a company called Kiva Systems. So if you go in an Amazon warehouse, there are today no humans. There are robots that take packets from the trucks to the shelves and then back. And what they have done is essentially engineered a lot of the hard problems away. So inside the warehouse, there are no human beings, so there's nothing to mess up your plan, your path. The communication is perfect. They have Wi-Fi going around. There is perfect localization. Every robot, every millisecond knows exactly where it is in the warehouse, right? So what we said is, well, okay, this is great. It works today. What would it make to take this from that controlled environment to the real world?
Sure.
So think of
To my house.
to your house or on the highway, right? You have cars. You think there's a lot of high-profile stories about autonomous cars. One of the big challenges there is intersection, and people are working on intersection protocols. Can we get humans out of the loop and try to make cars go through intersections without bumping into each other? And as we started thinking about this, we sort of came across two classes of properties that, first of all, the DART sort of term emerged, distributed adaptive real-time systems, because things have to happen
They have
in
to
real
adapt.
time. They have to adapt, and they have to happen in real time. And secondly, we realized that there are two classes of properties that these systems must at least implement. One is what we call guaranteed properties, no collision. The other, the flip side, is the mission critical properties. For example, for cars, you need to have a certain amount of throughput, right? A perfectly safe system is where no car moves, no collisions, right? And that's a great way to achieve your guaranteed property, but it's not ideal. It's not useful.
Doesn't achieve the goal state.
That's exactly.
I want to get here.
Exactly.
And it's not just throughput. I mean, it could be also deadline. It could be like, so if you have ambulances, for instance, going through an intersection, you want to prioritize that. So a lot of intersection protocols have this criticality idea.
That's
where
correct.
some traffic going through is more important than others,
Sure.
and you kind of have to prioritize that, and that's kind of something we've incorporated into DART as well.
That's correct. And what we realize is there's a two fundamental difference between these. One is the guaranteed properties are absolute. They must always hold. And the best, the mission critical properties are probabilistic. You don't want to know, can I always have 1 million cars go through this highway every day? The answer is no. If there's a big congestion,
Sure.
if there's a earthquake or something happens, no. But the issue is under assumptions about the uncertainty in the environment, what probabilistic guarantee can you make?
Okay.
And that's really important from the mission planner perspective, or people who are trying to design these missions, is can I get to that?
Right. Is
get
the
to that
probability
state?
high enough
Is
that
the
it's
probability
worth
high enough?
actually engaging in this mission? Is a
Exactly.
big question that's always
Exactly.
asked.
And in fact, going forward, some more interesting work is, if it's not high enough, what can I do to make it high enough?
A
these are
degraded
all,
situation.
Exactly. So these are all interesting problems. And so from that kind of DART emerged, and we basically said, let's create a process, an engineering process, right, by which we can build the software in the right way, starting from the right abstractions, and apply the right analysis to make sure that they have all the properties, and then finally demonstrate that on some actual platform to know that what we are getting is actually correct, that it can work with real systems.
So there's the possibility that some of the capabilities that James has been able to produce would violate some of the properties of a model checking, of a safe, I'll call it, of a safe algorithm. And so this is really where the collaboration comes in terms of understanding how the capabilities need to be formulated so that they can be verified formally and proven so that we can take them out into a world that is very uncertain and very unsafe.
And I think one of the things that was kind of mentioned might not be quite what the meaning we meant to say. Like, this isn't taking the human out of the loop. In a lot of cases, it's really extending human capabilities, and it's also kind of falling into the human on the loop kind of paradigm where the person can intervene if things go badly. So in the Amazon warehouse, there are people there, they're just on the floor.
Right.
And so they're supervising the behavior of this. They're making sure everything is done correctly, that orders are being shipped correctly, and that nothing is broken. This is the same thing for traffic. I mean, in the United States, we don't expect to have a fully autonomous driving fleet. Like, not everyone's going to do this. I mean, we're Americans. This is my car. I'm going to drive it, that kind of thing. And if you're building that kind of thing, an intersection protocol, you have to take it into account that humans
Sure.
are a part of this. There's variability. It's not going to be perfect. Everything you've planned for is going to be ruined at some point, and you have to be able to adapt to that. And that's part of the adaptive part of DART, is being able to adapt the environment. So like Gabe Moreno's work and things of nature, where it's adapting to danger and things of nature that comes into account.
So the guaranteed behaviors are the ones that are really mostly about safety, security, those kinds of things, and then everything else is probabilistic.
That's right.
So if something is happening in the environment that would cause you to violate one of the guaranteed properties, you have to adapt. That's the real-time adaptation.
And the other thing to understand is a lot of this is like, a lot of the verification happens in kind of a piecemeal manner where you're like, in perfect conditions, this is the kind of adaptation or this kind of guarantees you can give. And then you have a different scenario you test, like if there's an enemy present, or like, for instance, for adversaries, like when you have adversarial AI, like you would change your entire behavior
that's present
for that.
in the intersection.
Right. Which is kind of adversarial. A person, a person thwarting your best efforts, your optimal efforts, is kind of adversarial, and that's how AI kind of treats adversaries. It's not necessarily a nefarious person. It's just a person who's kind of ruining your good day. That kind of thing is how adversaries are.
So humans actually
They have a different goal.
They have a different goal.
Yeah, humans actually play two roles, right? Like you said, they can be a supervisory role, but they're also adversarial. They're also part of the uncertainty. And they are both. And so from the DART perspective, we sort of, even though we haven't specifically looked at human behavior, sort of the way we would bring in a human behavior is another uncertainty, another person that's providing input to the software, essentially. And but we haven't actually gone that far. I think it'll be really interesting to see how that might work out. Part of the challenge there is we don't have very good models of human beings. It's one thing we cannot treat a human being as completely non-deterministic because none of us are like completely random. We have rationality, but yet we do make mistakes. And so we have to model humans in the right amount so that the analysis we produces the right kind of results. They're not too pessimistic, not too optimistic.
Well, I would say even smart people act irrational sometimes.
Sure.
And when I've had quadcopters flying in the hallways at SCI, I've had PhDs walk up to them and put their hand in the blades. So I could have never predicted that before that happened. But I mean, even smart people sometimes do dumb things.
Right.
And
That's true.
and so even when you're thinking of rational actors, and this is something that's a very core concept of AI in general, is that rationality is very relative. And what's really interesting is some of the work that we've done in Dart kind of looks at parts of your algorithm or parts of your system that you would not have anticipated. So like when we're talking about like a statistical model checking for swarms, there's another one that might have a blog sometime. But one of the key things, one of the most interesting results of that work, I think, was the input attribution.
Yeah.
And the ability to essentially look at this algorithm and just from the variables that are being implemented, the environment description essentially, it can tell you why the mission would fail and why.
Wow.
Like point to something like to say like, your algorithm is not going to block, like for instance, we had like a defensive scheme, a paparazzi scheme where we're trying to block a photographer from getting a celebrity photograph, I think with these drones that are getting in the way. They're just occluding the photograph, right? And so we were doing analysis on that and we saw that it's really only 2 agents. We were like adding more and more agents to it. We thought, well, let's just put a swarm of drones out there in the simulation and 100 drones and see if it makes any difference. And there was no difference between doing 100 drones versus 2. And the reason for that was the algorithm itself was setting the first agent, on line of sight between the photographer and the VIP, and the next one is where it might be going. And so basically the one that's currently in line of sight and the one that's next to it where it would block the next line of sight are the most important things. So how fast they get into position and how they move, how fast they move is the most important thing. So we saw that just from looking at the input attribution, which is...
So one of the things these models are doing are helping you to identify non-intuitive conditions that either need to be accounted for or don't need to be accounted for. I don't need 100 drones if I can put them in the right place.
Exactly.
Absolutely, and like I said, for my dissertation research, I was very interested in emergent behavior, and this is kind of the definition of emergent behavior, where you have usually it's emergent misbehavior. You really don't get upset about emergent good behaviors, right? If all of a sudden you get $1 million from doing your job and it was not unexpected, that's a great thing. But what most people complain about or talk about is emergent misbehavior, where you designed a system for something specific, and then out of all of that came like thrashing or something else where nothing worked over time, and you don't know why it is. And so if you have a technique, which we think we have a good starting block for that can tell you what can cause thrashing or what can cause this kind of bad emergent behavior before you even deploy it, that can help you solve the problem before you start getting in trouble with clients and with your customers or with loss of life even in these cases, because these are cyber-physical systems working in conjunction with people. And that not only brings a monetary value to it, but it brings like a life value to it with more automation.
So if we step back a little bit and look at the Dart process, some key ideas have emerged. So there are 3 main aspects of Dart. And Dart actually brings together 2 paradigms that have been there for a long time in software engineering and in sort of formal analysis. One is a model-based development. So you start with a high-level description that's well defined in a language whose semantics and syntax are well defined, and the other is analysis, that you basically do analysis at each step of the compilation process from that high level language down to binaries. And so you see this, for example, in a compiler. When you compile code, you have, if you're writing in whatever language, the language is well defined, and then the compiler actually does key analysis and gives you warnings and says, and that rules out a lot of the errors that happen in the program. It doesn't rule out everything, but it rules out a lot of the errors. And so in Dart, we have a very similar compilation process. We have a domain-specific language called DIMPLE. It's another acronym for Dart Modeling and Programming Language.
These are recursive acronyms. There's Dart and there's DIMPLE.
Got it.
And so we use DIMPLE to sort of program the Dart system. We actually combine DIMPLE with another language called AADL. I'm sure you've had other
Architecture, Analysis, and Design Language.
Exactly. And they work very complementarily. So AADL kind of gives you the high-level architecture of the system. DIMPLE gives you the low-level code, like what actually happens in the protocols and the guts of the system, right? And so once you have that description of the Dart system, you can then start doing analysis. And we do 3 main kinds of analysis. One is real-time scheduling. We have to make sure that all the threads have enough CPU cycles to run, because otherwise all the other analysis is meaningless in cyber-physical systems, right? If your code doesn't run,
if you're late, you're gone.
Exactly.
In some cases, I mean, we have some concepts of criticality, like we were saying, that essentially there are certain things you might be able to preempt, like that aren't as important as others, but there are some that are mission critical that you cannot, it has to be schedulable.
Right.
And then there's some that kind of fall off the wayside, and that's okay.
That's
and that's like very common in a lot of UAV applications where you have like movement and things that are like flight, for instance. That is something you definitely have to schedule. It has to be schedulable. And then there's what's run on top of it, like analysis or something else, so where it's like taking sensor inputs and trying to figure out, was there a person there or something like that. That is usually important for like search and rescue, but it's not as important as keeping it airborne.
Right.
And a lot of this happens very naturally. Like if you have a UAV that has a lot of different sensors, and like for instance a lot of video feeds even, and you're running some like OpenCV on it, and you're trying to analyze the images in real time, then you have a really high computational overhead if you, like, for instance, notice 3 objects. So like if you pick out there's 3 objects and it has to run on there. Like before that it had no objects, so it was fine. Like the flight was working fine, the controller was working fine, it had plenty of CPU, and then it went over these 3 objects and all that started kicking up, and that's when the scheduling problems started happening. So that's what we have to deal with, is the mixed criticality of this situation.
And that maps very naturally to the properties that we were talking about. Remember, we had the critical properties, safety critical properties, and the mission critical properties. So it turns out that in general, the guaranteed properties are implemented by high critical threads. And the mission critical properties or the probabilistic properties are implemented by low critical threads. So when push comes to shove, you kind of can go degraded on the low critical properties, and you can still perform, but you have to preserve the safety properties, the guaranteed properties. So that's one part, the timing. Then comes the software model checking. This is proving that given that the threads have enough CPU cycles to run, they are doing the right thing. So this is where we analyze the collision avoidance protocol. So James and I developed a collision avoidance protocol as part of our original MCDA project, and we've been sort of just using variants of that protocol in Dart, and it's worked very well. And we can now, we have software model checking algorithms that can prove that the protocol is correct, not just for 2 drones or 3 drones, but for an arbitrary number of drones in an arbitrarily large area. Yeah, so that was really exciting for us, is to be able to make that contribution. And we could only do that because the language, the DIMPLE language in which the protocol was expressed, was restricted. It was rich enough to enable to express the protocol, but weak enough, restricted enough that you could analyze it. As you know, in verification, we often have the state space explosion problem. So if the language you're trying to analyze, like C or C++, is very complicated and it's very hard to prove anything formally. So in DIMPLE, we kind of had this right balance between the two, the expressibility and the verifiability. And the third thing is statistical model checking. This is what James has been referring to quite a bit. This is for analyzing the probabilistic properties. So now you have this complex system. How do you estimate the probability of finding all the objects on the ground given certain probability estimates and given some mission parameters? And that ultimately relies on lots of Monte Carlo simulations. So it's a statistical approach. So it does lots of Monte Carlo simulations. But from those simulations, using statistical hypothesis testing kind of results, it can give you an estimate of the thing you're looking for, the property you're looking for, and an error bound. So that's the important part, right? Because simulation is ultimately incomplete. All our estimates have error bounds. But the good thing is we can do enough experiments, enough simulations to make that error bound as small as we want. So I can tell you, for example, that, the probability of completing this mission and detecting at least 80% of the objects is 0.9 with a plus minus 0.05 error bound, right? And naturally what happens is, if you want to get the error bound small, if you want a precise answer, you have to do more simulations. But we've been able to do research in techniques called importance sampling, for example, that essentially allow us to estimate rare events, low probability events, with fewer simulations.
So you've incorporated the black swan kind of idea.
Exactly.
The very low probability but high impact.
Exactly, the black swan idea. So the idea is we can use importance sampling to estimate the probability of black swan kind of events, but using fewer simulations. And there's a lot of technical details behind how this works, and we have like publications and stuff.
There's another pillar of this that kind of glues everything together, and that's so you can run all the simulations you want. You can run 1 billion of them if you wanted to get your error bars down the wall. But if that system is not implementable in the real world, if there's nothing that actually, so you've got this high-level modeling language, DIMPLE, right? It can go through this process and generate, but if it doesn't work in the real world, then you basically have a lot of proven nothing, right? And so kind of where I come in into a lot of this is with the middlewares that I've been developing. I don't know if you want me to spell out these because Madara and GAMS, but essentially what they do is they bring in a quality of service to everything that happens within the system. And so everything from threading, like the computation assigned to threading, the epochs that are available for that, the communication itself, how does communication work, how does messaging work? When you receive something, what does it mean? Like, is it an all or nothing process? Is there a partial? So we had to have very specific semantics for every aspect of how the distributed system might work, and that's the only way we can really do verification. Because if you can't just use it for an arbitrary
you've got to set a
communication.
boundary on the state spaces, as you were talking about earlier, or else you're done.
And you also just have to know, you have a consistent view of the world. And so part of this was designing these middlewares to be more verifiable, right? And so a lot of this process was designing quality of service that could be implemented in a way that gives more confidence in the distributed system, not only from scheduling, but from messaging and threading and all kinds of other things. And so all that kind of glues everything together so that we have this transition path from this formal language, this dimple language that takes distributed processes and then guides it all the way through to the real world and real robotics.
So this idea of sort of multiple layers of analysis, but analysis that focuses on different things, that's something different than what we've seen in terms of a process that goes from model all the way out to implementation. So that's very exciting. And is that what you would consider to be sort of the major achievement of DART, is to be able to prove that that's a feasible thing to do?
Yeah, I think that's definitely one of the major accomplishments, is how do we bring these analysis in a semantically coherent way, and then how do we actually tie them together in an implementable system. So, like James was saying, we couldn't, when we were designing Dimple. By the way, I cannot overemphasize the importance of the MCDL, the project, the one that preceded DART. It turns out the Dimple language is also a play. In MCDA, we had a language called Dazzle. And the Dimple was essentially kind of a child of Dazzle. It was many of the concepts we got, like what should be the semantics of communication between two distributed agents. It's actually a non-trivial problem, especially if you want to say, this has to be implementable. It cannot just be something that's nice to model, nice to analyze. Unless we can actually implement this using a middleware, there's no point in doing this analysis. Then our analysis is all happening on abstract systems that have no real counterparts. So that was a no-no for us. So right from the start, we had this idea that our protocols and our semantics has to be implementable, and that's where sort of James and the rest of the team, we kind of had a complete collaboration, because every decision we made about, should it be shared memory? Well, what does shared memory mean in a distributed system? Because you have no central place. It's not like one processor. Well, so there is consistency. Well, what kind of consistency is it? So James would come in and say, we have a consistency based on Lamport clocks, where you have certain well-defined notions that earlier values cannot be seen after later values, etc., according to some logical notion of time. Not, we don't have clock synchronization and so on and so forth. So, that was another, I think, a big part of the project. So when I talk about DART, I have a pie chart kind of a slide on DART that kind of brings together all the different areas where people had to contribute. And the fact that all of them played together nicely to have a system where we can have demonstrable code that goes down to binary and zoop, we can actually see things running. I think that's amazing. And I think, to me, I know of no other project there that can do that level of integration of different techniques in a demonstrable way.
It was also kind of a nexus of just the kind of critical mass of researchers that were specialized in these fields coming together that probably aren't available anywhere else in the world. I mean, we had formal methods people, we had real-time scheduling people, we had middleware and artificial intelligence people, and all of them were put together in the same place at the same time, which is kind of fortuitous because, I mean, Sagar and I are pretty smart people, but by ourselves we would not have been able to accomplish everything we did in DART. I mean, this is not only are the capabilities there, but this has been made open source. So like DART is open source, Madara, GAMS are open source, MCDA was open source as well. So that's something that we've been able to do pretty consistently with all these projects, which means that, this means that people can use the research, not just read about it in paper, but they can actually download it and do this. And we've actually given some tutorials recently to the Air Force research labs that showed them how to build a distributed system from the ground up, and some of them had never made a distributed system ever or even programmed before. And so within an hour, they were making a swarm of UAVs that accomplished a mission, which is pretty cool to see in action.
Well, and that's, I think, one of the things that draws me to what you're doing is that idea that we're going all the way to implementation, and you can see on the water, in the air, the result. And as somebody, you know, just out in the world, building confidence into these devices is huge.
Yes.
You know, to be able to get adoption of any of these human extending capabilities. You know, in military, in certain other settings, you can kind of mandate you will use this, but you can't tell me, you know, U.S. citizen, you know, Susie Miller, that I must have an autonomous vehicle right now. Now, maybe someday in future, but I have that choice. And if I'm going to make that choice, I have to have confidence in what I'm using. And these kinds of techniques are critical for us to build the confidence of the whole population that these are safe kinds of cyber-physical systems to use to enhance our lives.
And we've seen some really, you always see the bad headlines. You don't see anything really good about autonomy in the news. I mean, like, you know, you had the recent Tesla crashes when they were on autonomous mode. And so this became news items because people are worried about the safety of these systems. And also we're trying to prove that this is possible, right? So we're at the very beginning of autonomy being pushed into like the consumer space and having people able to do this. It's not just in industrial settings where you have these big multi-million-dollar robots that are doing some complex tasks, but they're doing something that's very small. We're having like machines and autonomy being pushed into the real world and interacting with human beings in a way that's beneficial, almost always, but also can be dangerous. And so you need this kind of approach. You need an approach like this that gives you safety assurances about this so that people can start to trust the autonomy and be able to use them and be able to be more effective, because that's what the point of autonomy is. It's not replacing people as anything. It's making people hundreds of times more effective in some cases, which we think will be beneficial for the economy, for the DoD in various ways, but really for people, for the humanity.
So often when you talk about confidence, right, there are two kinds of things. You see a lot of academic publication happening in every conference about verification, about cyber-physical systems. But I think to a common person who is a consumer of these technologies, that doesn't give confidence, because often that is sort of esoteric academic publication. How many people actually go and read and follow this technology? They might hear sound bites. Often what gets confidence is when they actually see the thing happening in practice. So when they actually see Google driving around these cars, and Google publishes some statistics, or Tesla publishes some statistics that, we ran 1 million miles, and look, there were no accidents, right? Or we ran 1 million miles and there were only 2 accidents, and etc. That gives us confidence. And I think with DART, and in particular the research we are doing, we are trying to bring together both those ideas, because we need mathematics, we need the exhaustive analysis. 1 million miles is nothing, 1 billion miles is nothing. If you calculate the total number of miles driven by US drivers in a year, it's like trillions of miles. So the fact that you drove 1 million miles and that it shouldn't really give you a confidence. What should give you confidence is that, together with the mathematics, the analysis, the exhaustiveness of the nature. And to me, what has been missing is something that's bringing together both. And that's because the way we are set up, we have researchers working, or academic researchers working on the publication side, and then they kind of stop and they expect the technology to somehow jump to the practice. But the practitioners, they don't really have time. Like, you see this even in like universities. You have groups that are heavily experiment focused, right? And all they do is like build things and they run, but they don't really do a formal analysis. And then they have trouble in the demos and stuff. And then you have the formal people who are doing this mathematics and this and that, but they don't really talk to each other.
And they don't get to a demo.
They don't get to a demo. And I think what we are doing, and what the ACI is uniquely positioned, is to be this bridge, is to be the connection between X here and Y there, and also add our own expertise. And I think we are uniquely situated. So right now, James has already started this process. His research has been heavily focused on demonstrating his techniques on real hardware platforms. And we are kind of taking that cue, and we are continuing that. So we are building sort of a drone lab. Let's not call it a drone, some
cyber-physical
CPS lab inside in the what used to be the ACI library. So please come by and see what's happening there. Where the idea would be to continue that thing and then be able to demonstrate our research on other platforms, especially things that fly around, and so we're trying to do this because we can do it indoors and we don't have to rely on the GPS for good. But I think that is a unique role that the ACI could play, is to bring together ideas, transition ideas from academia to practice.
That's our mission.
That's our mission. And I think CPS is one of the best domains to be able to do that, because you have software with the physical world. So you have the intangible with the tangible, and you don't see that in many other domains.
By the way, I mean, we kind of started using some terms I don't think we defined earlier. CPS is cyber physical systems, and cyber physical systems are a lot of what we've been talking about. It's like the marriage of hardware and software, and the ability to control and do that. It's not like a cyber warfare thing. It's not anything like this. We're talking about very specifically hardware platforms that you're controlling with software and you're making intelligent, generally. So that's what we mean by
embedded.
CPS.
It used to be called embedded, real-time embedded systems, and it got morphed into.
We have to have a new term
Yeah.
every 10 years, whether we need it or not.
Well, when Congress stops doing the funding, that's when they tend to come up with a new buzzword.
That's been known to happen. So what's next? You finished this phase of the project. I'm sure you have ideas on what you want to do next, and what do you have in your plans for the near term?
Sure. So one aspect of this is another project that we are just starting. It's called Certifiable Distributed Runtime Assurance, and it's not as cool as Dart. It's CDRA. But the idea is actually really cool. So the idea is you are going to have complex systems that are going to be impossible to formally verify. You have a machine learning component. Like, think of an autonomous car. It's going to have components in there that are going to do extremely advanced computation and that are extremely capable, but fundamentally unpredictable. So most of the time, it will give you tremendous capability, like your Google Maps, right? Like almost all the time, it gives you this nice way to get you home. But then in the back of your mind, you have this nagging suspicion, oh, what if it's taking me through an area I don't know, that kind of thing. So we have to live with that power, with the unpredictability. And the way we can do that is to put a monitor, a guardian, as a trusted part in software and in the system that's going to watch over this powerful but unpredictable rest of the system and stop it from doing really bad things, right? So this idea actually emerged at the SEI. It was called Simplex. So Luisha did this, a bunch of other guys did, but in the control domain. So you had a powerful controller and you had a trusted controller, and if the pendulum was falling down, then the inverted pendulum was falling down, the controller would, the monitor would switch it back to the trusted controller, and there's a lot of analysis about when to switch, how often to monitor, etc., etc. And then what happened was recently the Air Force Research Lab, AFRL, picked up this idea and they called it runtime assurance. And they enlarged this idea to not just control, but to any kind of system, right? So you basically have to put the monitor in the right place and to make sure that it stops the software from sending bad commands across what I call the cyber physical boundary. So the software can do whatever it wants to do, but at some point it's going to actually actuate. It's going to send a command and say, now affect the physical world. Like move this arm, open this door, drop something. What the monitor does is make sure that those actions do not happen under very specific circumstances. And our research here is actually how do we build a trusted monitor? How do we verify that monitor? And the good news is the monitor can be simple. So the rest of the system can be very complex, will be very complex, and will be unverifiable. But the monitor can be engineered to be really simple. But we have to still do all the verification, and it has to be performant. It cannot monitor too many things. If you put too many checks, then the rest of the system comes to a halt. So there is this balance between verifiability and how much you interfere. And finally, we have to put the monitor from a security perspective to make it uncircumventable. So if somebody hacks into your system and tries to disable the monitor, that should be physically, that should be impossible or as close to impossible as possible. So we have a security angle in this research where we have an attacker model. What can an attacker do? And then under the attacker model, we should be able to prove that monitor cannot be taken over, or if it is taken over, it will, before it gets taken over, it will do some default action like, bring the system down to a safe state, etc., etc. So this is really exciting. I think we're just
got your work cut out for you on that one.
we are looking for, it's part of the reason we want to demonstrate. So actually one of the examples we have for this is what we call a virtual tether. So remember in the beginning of the program, we talked about how these drones, they'll often jump to the ceiling. One of our colleagues, Scott Hissom, he said, well, I'm going to bring a fish line. I'm going to tether that thing so it doesn't jump up. And then we thought, well, what if we can use a monitor as a virtual tether? Suppose we can actually have good localization and we can put a monitor and say, no matter what happens, so if I give you the RC controller and you try to push the monitor up to the ceiling, the system, the monitor is going to watch and above a certain height will cut it off. So one of our goals actually is to do a demonstration of this and to say, here in the library, here is the sort of the virtual area within which it cannot escape this area, and try your best to do it. And so we're going to give you the RC controller and try to do it. And that'll be sort of a
It's a
demonstration.
Maybe
little
we'll
more,
have to
yeah.
come and film that when you get a little farther
Yeah,
along.
absolutely, absolutely.
Yeah, and the what he's talking about, the monitor, is a little more, I guess, invasive than you might think. I mean, it's not just intercepting human commands to tell, like whether it goes left, right, up, down, whatever like that. It's actually at the flight controller level. So we have to intercept the ability, like, because like we said, I think before the interview, there was no taping going on. We were talking about the quads flying into the ceiling or flying anywhere they felt like going. But essentially, I mean, when I was doing quadcopter research, I did actually, when I was outdoors, have some situations where I would tether them with fishing line to stop them from going wherever. And that was to keep us safe and also keep the drone safe, UAV safe. But to actually stop the flight control from this, because it wasn't a person causing it to fly out into nowhere, it was the flight controller itself. Sometimes it's just wrong. It's implemented, it has bugs in it, various other things. And so a part of what we have to do in that project is to invasively put monitors inside the flight controller to say the flight controller might be pushing this out, not just the user.
And when and where and why and
Yeah.
justifying that is going to be one of the research questions.
That's
right?
correct. That's correct.
And I think from my interest from this one especially, I mean, I don't think we're addressing this year or this project, but essentially there are a couple things about Dart that are limiting as far as what kind of systems you can build. One of them is asynchrony. So like it's, we tend to force a synchronous model of computation on the distributed agents in Dart. And what that means is everything has to barrier together when they're doing a mission.
Right.
So like if they're moving together, they're kind of waiting for each other to come to a certain mission state, and then they move to the next mission state together. Or they can do it, they essentially can move asynchronously to the next mission state, but there's still that barrier
Right.
on the mission state, on where they're going. And this is very limiting for a lot of real-time applications, especially outdoor robotics, because things lose communication for a long period of time in some cases, and we have to figure out how to make things more asynchronous along the gradient from synchronous to quasi-asynchronous to fully asynchronous.
Okay.
And so that's still an open problem. It's something that I don't know if we even have something slated this year to look into that, but it's something that we knew in Dart that was going to be an issue with making all systems verifiable.
Right.
And it's one of the reasons we started looking into statistical model checking and other things like
Sure.
that, so that we could say, look, it's going to be deviating from this perfect mission state. We just need to handle it in some other alternative way.
Yeah.
It's good to know that you have work ahead of you.
Oh yeah, and
You're not going to be finished anytime soon.
The other thing is, so when we're talking about this monitor, he's talking about a simple monitor, and he's talking about making it not too complex that it would interfere with itself. But also, I mean, there's this Turing level problem, which is essentially if you make these simple monitors and you make 5 of them, let's say on a UAV, how do you compose them together to have this kind of verifiable monitoring between 5 different things? And that's, like I said, that's like Ed Clark and Joseph Safaki's ++. This is like higher level verification that's not been done before.
Yeah, so that's on our trajectory. It probably is, like you said, not going to be till the second year of the research.
One
but
step
I think
at a time.
One step at a time. But I think there's a big role for sort of middleware and the AI technology to play there, because there's no reason that we cannot engineer the middleware to actually help make the monitoring simpler or make the monitoring more tractable. And I think that's to me the beauty of one of the nice things technically is finding this balance between verifiability and capability, and that's I think
That's the crux.
Yeah.
So I know that there are some folks out there that are probably going, where do I get my hands on all this stuff? You said you have open source, yay, but what are some key resources for software architects, cyber physical system developers that they should look at in getting educated about Dart and what its boundaries are, as well as what's been accomplished?
So the Dart system is open source. It's publicly available on GitHub. I think we can make a link to that available.
We'll make that
online.
available.
Okay. So you have the full source code. You have tutorials. You have instructions to download and compile. You have various videos showing what kind of simulations you can run. We've actually tested it extensively within the group and across some sort of known friends, and it's worked very well. So we largely support the Linux platform, but it's worked very well on Linux. So Dart actually relies on the Medora and GAMS packages that James develops, and I think, James, you're probably the better person to talk about how those are available.
Yeah, so we'll obviously provide the URLs for the Medora project and the GAMS project, and how they interact is described in a lot of different wiki pages and PowerPoints on there. There's also, I'll try to make sure you guys have a link to the tutorial series we gave to the AFRL, because I have all of the slide decks we use for giving that tutorial on the GAM site. And that kind of walks people through the installation of it, which we've tried to make into just a one-line command thing that you can do on Windows or Linux. And Medora GAM should work on most platforms.
Okay.
I mean, Apple iOS, Android, we've had Android running on the boats before. And basically every operating system I can think of. Essentially, if there's anything, if ACE, which is the adaptive communication environment from Doug Schmidt over at Vanderbilt, which has been around for 25, 30 years, if it can run with that, so even old Citrix servers, basically, you can run on that if you wanted to, Solaris, whatever you want to do. But essentially, it runs on most platforms, hundreds or maybe even thousands of platforms, ARM, Intel, things of that nature. And so all this is kind of described on the wiki pages. We'll provide some links for you. And essentially, if they just follow the tutorial, the first slide will show them how to install, and then if they can go to the specific tutorial they want to, like build algorithms, for instance. If you want to learn how to do distributed algorithms, you can do that. And then we also have some papers. I don't know if we could provide papers, but that
all those kinds of resources. We'll give you links to the digital library and all that.
Yeah, the DART website, I think, actually has also a publications page where we talk about some of the papers.
Excellent. Sagar, James, as always, it's fascinating to talk with you. I love being able to catch up and sort of find out where you've gone ever since you have both come here and talked about some of your initial research. I'm really thrilled to see you being able to work together and bring together some of these great ideas. So thank you so much for sharing this. We have a blog post on this topic also, and so that will be available at insights.sei.cmu.edu. That's where we have all our blog posts. And James, I think you're the lead author on that, so James Edmondson is the name to look for. And we will provide resource links throughout the transcript to the things that you've talked about. The podcast itself is available on the SEI website, as I said at the beginning, at www.sei.cmu.edu/podcast. It's also available on the Carnegie Mellon iTunes U site. So once again, thank you for viewing, and thank you again for sharing all of this wonderful information.
Thanks for having us.
Thanks for having us.